He is planetary geologist who use spacecraft data to study the surface of planetary bodies. He specializes in the technique of the reflectance spectroscopy of minerals and frequently integrate multiple data set derived from various techniques to carry out his research. He has obtained his bachelor, master, and PhD degree in geology from Delhi University, IIT Roorkee, and Brown University, USA, respectively. So, other guest is Christian Wohler. So, he's professor of image analysis at Faculty of Electrical Engineering and Information Technology of Dortmund University of Technology. His main scientific interests is in remote sensing, photogrammetry, and computer vision, with application in the field of the planetary science and exploration as well as in industrial domain. So he received his diploma equivalent to MSc in physics from Wohler University in 1996, a doctorate degree in computer science from Bonn University in 2000, and habilitation in applied computer science from Bayfield University in 2009. So he's Dart Fellow, and they are observing from our 1.04 centimeter, but they are interested in the polarimetry of the surface of the moon. So now I request Dr. Dhingra to speak on the title he has proposed.
Audible? Thank you, Santoshi. And before I start, I wanted to express my gratitude to Aries, especially the director, and Santoshi, and the two students who have been accompanying us for the observations. So, as was introduced, that both me and Christian actually works on a lot of things. I dominantly work on the moon, and we thought we will take this opportunity to share with you some of the excitement that is associated with lunar science. So what I will do is I will spend the first half kind of introducing you to the moon. I am assuming that not a lot of you have worked on the moon. If anybody is there, can you raise your hand if anybody has worked on the moon? Okay. So I will introduce the moon, highlight why we should study the moon, and then I will give a few examples from my research. From there on, since you will be kind of aware about the lunar landscape, Christian will take over and discuss some of his research results in a little more detail. So this is, one view of the moon that we can observe. Part of it we can observe from the Earth, and part of it we cannot. The on this side of the image we cannot really see it. This is called the far side. But on my side is the view that we can see. And if you really gaze at the landscape, there are a lot of things that will attract your attention. For example, you see these dark regions on my side, bright region on the other side. In the bottom, you have this kind of quasi-circular feature which has dark material and bright material. And then the entire landscape is dotted with these bright specks. Some of these bright regions also have these elongated bright streaks. So we'll be talking about a lot of them in this talk. So let's get started. So when we think about the moon, although all of us see it almost every day in the night sky, at times we don't appreciate enough how much the moon is important to us. So when you think about the moon, there are many different ways depending on how do you associate with it. One view is this taken by Apollo 8, which is the image of the Earth taken from an orbiter around the moon. And in fact, this was one of the first images which led the humanity to understand that all of us are located on that blue planet. So this is something that we know from the moon. Staying on Earth, we cannot really see this view. So Earth's closest neighbor is the moon, but not only in terms of distance, it is also in terms of time. It has been there almost ever since the Earth was born. There's a very slight time difference between the birth of Earth and moon. And as a result, all the things that have been happening on Earth, moon has been a witness to it. And so there is this motivation that a lot of events that happened on Earth also happened on the moon. And so moon becomes important. It has influenced the Earth in more than one way. When we think about the size of Earth and size of the moon, moon is actually quite large compared to other satellites. As a result, the moon has influenced the rotation of the Earth. It has gradually slowed down the Earth to the current length of the day. It has controlled its axial tilt. If you have large axial tilt, then there can be large variations in the temperature across 1 year. So that has implications for life. We all know that it is the gravity of the moon that causes tides on Earth. And finally, a lot of life forms, their biological cycle is actually governed or affected, influenced by the moon. So moon is linked to us in more ways than what we think of. As I was saying, that moon has almost been there for the same duration that Earth has been around. So it holds a lot of records of Earth's past. Some of those records are direct, some of them are indirect. So the first one is the record of impact cratering. So things, all of us have started, all of us have learned that starting with a cloud of gas and dust, we formed planets, right? So one thing that has been happening all through is matter interacting with each other in terms of collisions at different scales. When it goes to large scale, we refer that to as impacts. So unlike Earth, the moon is kind of frozen in time because it is small. It lost its heat long back. So a lot of that impact cratering record, the impacts that have happened in the system are frozen on the surface. So if you want to look back in time, find out that at 4 billion years, 3.5 billion years, 2.5 billion years, what was the cratering flux? How many bodies were impacting? Moon can give you that answer. We also believe that part of Earth is actually contributing to the current moon. So part of Earth material is actually in the moon, and that in that way, it holds the record of the Earth's past. And lastly, in today's time, you may have heard that there have been a lot of missions that have been going to the moon and that are planned to go to the moon. Because of a lot of things, I'll not get into that, but simply say that when we think about the moon, it can act as our pit stop for exploring the rest part of the space. It can be our base station, and it can also act as a human outpost for carrying out research, including astronomy. So that begs the question that when we look at the moon, what is there to look at? So I have, randomly picked some features which you may associate with. Some of them may be new, but this gives you a perspective on what is there to be looked at when we see the moon. So I mentioned earlier on that there is a near side that we can see and there's a far side that we cannot. The near side looks very different from the far side, right? The bright regions are called as highlands and the dark regions are called as mare. Highlands are older, mare are a little younger. The mare represent volcanic landform, while the highland represent the original output of molten moon. So one of the most common things that you can see on actually any planetary body is a impact crater, and this is one variety of impact crater called a complex crater. Through the time, processes can actually change the configuration of craters, and they can adopt identity like this. where their floors can be modified. These are called floor fractured craters. Then we have these wispy, bright albedo deposits called swirls. Although a lot of studies have gone into characterization of the swirls, we still do not have a definitive answer to what these things are. When you are looking at these features, one thing that you should ask is what is the scale? So the scale is ranging from few tens of kilometers to few hundreds of kilometers. This particular, the swirl feature, the bright streak, is more than 200 kilometers across. Then you have this sinuous channel-like feature. It's called a rill, and it is formed by the flow of volcanic lava. And then finally, what we call as red spots. These are ambiguous in origin, but they are spectroscopically identified for a very long time. Even in our survey here, we have been collecting spectra of these regions. So you can see that there are at least a few things. There are actually dozens of things that you can look at, but this is just a sample of what you can look at when you are observing the moon. The next question comes when you are looking at it. Any of these features, you can ask this question: how did this feature form? When exactly in the time frame did it form? How long did it take to form? How common is this feature on the moon? Some of them are very common, like impact craters. Some of them are very few, like red spots. Does this feature also occur on Earth? That establishes the connection with Earth and other planetary bodies, and also emphasizes the significance. What does it tell about the history of the moon? We are not there just to observe these features. We are there to learn what these features have to tell us about the moon and other planetary bodies. And finally, these are basically the products of processes that have happened on the moon through time. So by looking at these products, we are asking the question, what processes were active in different time periods? So we start with the impact craters. One very interesting thing about these is they span a very large spatial scale. If you happen to pick a grain of sand on the moon, it will have an impact crater, and they go up to several hundred kilometers across. So this is a process that is not only pervasive across planetary bodies, but it is also occurring at variety of scales. What is involved in this? Basically, if you go from top to bottom, there are impactors of different sizes, which are hurtling towards the lunar surface, or in general, the planetary surface. As soon as they come in contact, they transfer their energy into the ground. As a result, there is a stepwise excavation of the material, forming a cavity. Material is pushed down, material is transported out to long distances, and some amount of material is melted. But all this, at all these scales, happen in a time span of like this. So it is so fast, it is very difficult to understand all these different steps. So one of the easy ways to understand that is to look at the moon, which is the natural laboratory of impact craters, to look at variety of them and understand which craters have what type of surfaces, which thing is more common, and then look at wide variety of craters to understand the cratering process. And that is one thing that we do very often. We understand the dynamics of impact cratering by looking at what we call as morphology of the crater. In other words, the landscape that we see. Why study impact craters? So all these yellow circles are of all different sizes are the craters about 20 kilometers mapped on the surface of the moon. And you can clearly see that if there is one thing that is basically overwhelmingly there, it is impact craters at all different sizes. So because it's a common landform, it has a significant role to play in the evolution of the planetary body. And so we should study that. So I give you this example. This is a near site crater, Tycho. You can see it with naked eye. It is in the southern part of the moon, of the lunar near side. So to give you an idea about the scale, it's about 85 kilometers across. So depending on where you have come from, just find out the distance from Nainital to that place, and you will get an idea how big or small this feature is. And these sizes are fairly common. In terms of what exactly do we see when I say we try to study the landscape, these are some of the for these type of craters. There are a wide variety of craters. For these type of craters, we have terrace-like features which form. There is a flat floor, and there is a central uplift or peak. So for scale, the peak is of the order of about a kilometer. That is significant, right? And all this happened in this. So you can imagine that how many things must have happened. And you would like to know, because from one crater to the other, for a given type, their landscape looks similar. So it has systematics involved. How do you really break it down? We look at images, which is the easiest thing that you can do, whether from your telescope, from your naked eye, or from a spacecraft. Any space mission that has ever been sent, they've put a camera because it is the easy thing to do. So what we do is we simply look at the terrain and try to classify it. As humans, we are interested in finding clusters, right? So we classify the area into things which we can define. So from left to right and top to bottom, you can see all these different what we call as morphologies or landscape types, which can be defined even in terms of their roughness, brightness, scale, a lot of things. Occurrence in clusters, occurrence in isolation. And then we basically map these onto the surface. So if this is the crater, we apply this classification scheme and we end up with something like this. What are we basically doing here? See the image that we are seeing. The image that we are seeing, it's a time compressed event into one image. From the starting till the end, all the events have been overlapped on each other. So you need to dissect that. How do you really dissect that? Tease apart things which look different. And then I give you one example of how this can be useful. So if anybody is interested, you can look at this paper or talk to me after the talk. So here, the yellow feature in the top is the one that I'm going to talk about. So that is Tycho. We are looking in the northwestern quadrant. This is our map. And that yellow feature is this image. Now you can also see in this map, it may not seem like, we have done much, but these are large scale features. Tycho is about 84 kilometers across. And then you ask this question, what these yellow arrows are pointing out. It seems like there is something that has climbed upslope. There is this blanket that is hugging the wall. So we believe that this is molten material that has moved. The scale is of the order of a kilometer. How can you push molten rock up a kilometer? So two ideas are there. We call them impact melt wave fronts. Forming of the cavity and filling it with molten material. Subsequently, in the evolution, you can have slumping. You have seen landslides here. There can be huge landslides, which can basically cause ripples in this melt volume, leading to providing energy for this wavefront to climb upslope. Another way is, remember I mentioned about the central uplift. So that's about a kilometer high and a few kilometers across. So if you are bringing this material up from several kilometers depth, it is going to displace the molten volume. And that can kind of do the same stuff, create those waves, which can then climb upslope. So here is a simple illustration as to how just mapping can highlight the process. And then you can go forward and test this out through experiments, through modeling, through observation at other craters. The second topic that I am touching upon is mapping of the moon in terms of its mineralogy. Here also we are interested in how the composition is telling about the past of the moon as well as the processes that have been happening. So we start with our near and far side. The change here is instead of looking at the landscape, we are now looking at composition. So when you look at this terrain in terms of the compositional aspect, we know that the bright regions are made up of just one mineral. It's called plagioclase. It's made up of calcium, aluminium, and silicon. Now, if you are a student of geology, you will know that on a planet-wide scale, if you have to produce just a single mineral, there is no other way but to melt the entire planetary body. So just this one piece of information that this is plagioclase, the bright regions, and it is pervasive all across the moon, tells you that the moon melted. Now then the question comes, how much of it? So then that gets into detail. But this is one example where the knowledge about what we call as global magma ocean came from the earth, and then moon is so small and the moon melted. For melting it, you need a lot of energy, right? So where will that energy come from? If the moon can melt, what about Earth? What about Mars? What about Mercury? So this concept then was applied to other planetary bodies. So when we are looking at different planetary bodies, we not only know about those, but we also get to apply the understanding from those planetary bodies elsewhere. And here the kind of thing in focus is mineral, which is plagioclase. There are a lot of minerals. So you can consider minerals as thermodynamic factories, which can be used as indicators of the processes, because minerals form under certain set of conditions. Like the landscape that we saw in earlier slides, here mineral is the product of the process, right? With that process might manifest in terms of temperature, pressure, and other things. So when you look at minerals, you can indirectly infer the process. So in this case, we are using the technique of reflectance spectroscopy. Sunlight falls on the lunar surface, gets reflected, and if you measure that reflected light at different wavelengths, you can identify the mineral. Here are some of the common minerals that we find on the surface of the moon. Some of them we also find on Earth. So minerals have signatures in the form of these bands, which are called absorption bands. So they have physical bases, and therefore they are considered as DNA fingerprint for identification of mineral. We use this for both identification as well as quantification of the mineral. And using this knowledge, we observe the moon in color like this. We code parameters using the spectra, and we invert them in terms of the spatial distribution of these curves. And the spatial distribution tells us a lot about what has been happening. So here is one example. This is again a near side crater called Copernicus, about 100 kilometers across. You perhaps now have some idea what we are looking at: the terrace, the flat floor, and the central uplift. So take a gaze at the floor and try to see what you can if you were going to map it. When you apply the algorithms based on the spectra, you find an image like this, something that you do not see here. So there is this S-shaped inverse feature. Colors represent mineralogy. So there is different mineralogy on the surface of the floor. And you cannot really see that in the black and white image. So what we are essentially seeing here is signature of impact melt, the molten material produced during the impact cratering event. And the largest amount of impact melt occurs on the floors. But so far, people have believed that that is largely homogeneous. And in this case, we find two different varieties of impact melt. So once you have that information, again, remember the scale. The image can fool you, but we are looking at 100 kilometers across. The feature is about 30 kilometers. This is the only known feature of its kind that we know anywhere, actually. But courtesy of the compositional information that we see here, it merits understanding in terms of how the impact melt dynamics happened during the crater formation to preserve these two different compositions of melt. And needless to say, because it is an impact crater, it has implications for other planetary bodies. In terms of the detail, basically the colors are representing these spectra. So now if you look at this particular figure, the dashed line, you will see there is a subtle difference in the band positions. That subtle difference, when you map it on large scale, it can tell you a lot about those differences. So we see this at 1 micron and at 2 micron. So wrapping up, when we are thinking about landscapes, the various geological processes which occur on planetary bodies, they can be understood by the products, the landscape that you see. These products can manifest in terms of, as I have shown you, morphology and mineralogy. Christian will talk about other aspects. When we carry out these systematic studies, they provide key insight into the processes that have led to those products. So you establish that link. And when we understand those processes, they have implications for other planetary bodies. This is what we have, what I have just discussed is just tip of the iceberg. It is something that any planetary geologist does, and that highlights what is there on the moon to be understood. And then I'll pass it on to Christian to take us further, showing other facets of the moon.
Okay, then I will continue looking at the spectral parameters with which Deepak already started to give an overview. A typical spectrum of a lunar structure in the Maro regions specifically looks like this. So this is a spectrum of a, no, we use this one, okay. In principle, it is shared. Let's say. Yeah. So this is a reflectance spectrum of a small impact crater in a volcanic mare area. And we can see that there's a general trend of increasing reflectance with increasing wavelength, which is that can be described, for example, formally by the convex hull, which is here indicated as a thin dashed line. Dividing the spectrum by the thin dashed line yields the so-called continuum removed reflectance, which is a very important measure in planetary reflectance spectroscopy, where we can see those absorption bands that are very specific for the minerals in the crustal material, much better than in the original spectrum. So what is very typical is one absorption band at 1000 nanometer wavelength and another one at 2000 nanometers wavelength around. And each of these absorption bands can be described by a depth, by a width, and of course by a position. That position, the wavelength, is equivalent to an energy that is in these cases usually not an electronic transition. Short wavelengths it may be, but for the longer wavelengths, these are rotational and vibrational transitions. If we compute these parameters for every pixel of a hyperspectral image mosaic, as has been acquired, for example, by the moon mineralogy mapper instrument on board the Indian mission to the moon, the first Indian mission to the moon, Chandrayaan-1, we get we can encode it as a simple RGB mosaic, where the red channel corresponds to the integrated band of the first, the left absorption band, the green channel to the integrated band depth of band 2, and the blue channel is simply the reflectance you are between between the two absorption bands. And that shows that we look at the cylindrical projection here. So what we see is a lot of blue areas. These are the areas that appear bright when you look at the moon, the so-called highlands, as Deepak already indicated. And the orange, red, and also greenish areas, those are the mare areas that consist of volcanic material, especially the mineral pyroxene, or the minerals of the class pyroxene. Obviously, the mineralogy of the highlands seems to be simpler than the mineralogy of the Maria. But that's nice, but one cannot draw any quantitative conclusions. So one can say, yeah, there is a bit more this or that behavior, but it's not really. We don't get quantities out of that yet. So what we tried was to extract. Getting strange messages here. The goal was to extract the abundances of chemical elements in the lunar surface based on these spectral data. One can say that, for example, the calcium and magnesium content of the lunar surface depends on the center positions of the two absorption bands that I've shown. And it's not fully physically understood how they depend, though. So in order to infer quantities, there's not an established physical model where you insert a spectrum and then you get out this or that composition belongs to that spectrum. The problem is much too ambiguous. But if we don't understand something physically completely, then we can use something like machine learning. The very simple form of machine learning is multivariate linear regression. That is a form of, so in nowadays language, one would call that machine learning. We put data in and get target variables out. Input data are the spectral parameters. Target variables are the elemental abundances. And as soon as there is some correlation between them, these regression techniques, not only the classical multivariate linear regression, but also more advanced real machine learning methods like support vector regression, are able to construct a model, not a physical model, but a numerical model to provide the target variables independence of the input data. One could also use neural networks. Others have done that before. Here, Xia et al. 2018, but sometimes it moves, sometimes it doesn't, and this device vibrates. Maybe the battery. Then I do it by hand. So one can also use neural networks for those who are in some form acquainted with that. And once the regression function is trained, one can apply it to full resolution data. One can apply it to full resolution data, and that yields a high resolution map of the elements that we have learned from the from reference data. Where do the reference data come from? They come from completely independently measured elemental abundance data, where the method is gamma ray spectroscopy, lunar prospector, gamma ray spectrometer, iron. That is simply counting iron atoms by counting the decay, the decays within the nuclei of iron atoms of different isotopes. And if you use that as the target variable, we obtain such a global iron map when applying the calculated learned regression function on the reflectance data and the inferred spectral parameters. So we see lunar Maria have much more iron than lunar Highlands. That contrast stands out very clearly. For magnesium, another very important mineral building element, the differences are less obvious. Yeah, there is a difference between Maria and Highlands, but here you can, for example, see that a large area which is partially covered by Highlands is also having a large magnesium value. And calcium is again, for calcium, there is again a very clear distinction between Maria and Highlands. Calcium occurs both in volcanic minerals as well as in the feldspathik minerals of the Highlands. Magnesium is present mainly in volcanic minerals, but shows strong differences regarding which minerals are considered. So different minerals of the class pyroxene that exists on Earth too have strongly different amounts of magnesium. And then comes one aspect: if we have near infrared spectra, as we do have here in those M-cube spectra, 3 micron, and maybe some of you did asteroid spectroscopy. Did any one of you do asteroid spectroscopy? Is there the same problem occurs? It's rather nowadays counted as an astronomy, still counted as an astronomical endeavor. So from a certain, depending on the temperature of the body, from a certain wavelength on, what we see as reflected, as the light that we see is not just reflected sunlight, which we are interested in, but also thermal emission of the surface. And in principle, that is a physically well-behaved problem, at least for a smooth surface. You have incoming energy, you have outgoing energy. There are well-known, there's the Stefan Boltzmann law, there's the Planck radiation law, and all these can be combined to compute the thermal emission component given a certain albedo of the surface, so a certain reflectivity, and the sun at a certain distance. in that way, for a smooth surface, there is a well-established framework that allows for computing a thermal emission component. It becomes much more different when we look at a realistic planetary surface, namely a rough surface, because we have facets of the rough surface that illuminate each other, heat up each other, and shadow each other. So they take away sunlight, they add sunlight to the direct illumination. That becomes very complicated. And one of my students last year finished, or more or less finished, but presented the first version of his thermal model of the lunar surface that we actually developed for applying it to infrared measurements, hyperspectral measurements of Mercury for the Bepi-Colombo mission in which we are involved. But for the moon, it works also fine. And the difference is shown here. So if we don't do any kind of correction of this thermal emission, here for a typical highland surface, we usually have this light red apparent reflectance, uncorrected. Our method gives us the black curve. That is a version of the method from 2017, but the most recent one gave some changes, but not too considerably. And the typical Mare spectrum without correction, here you can see very well the increase in reflectance, which is not at all due to the mineral properties or the spectral properties, but just due to thermal emission. And the black curve again shows the corrected spectrum. The intermediate, the pink curve here shows the corrected spectra on the, so I would say the official version on the planetary data system offered by NASA. And but for that data set, it was found in the last 7, 8, 9 years that that method was not really physically appropriate for doing that job. And what this is about, I should maybe explain. This this absorption band at 3 micron on the moon was very surprising. It was discovered in 2009, for example, based on M-Cube data, but also based on spectra from flyby missions that actually went to Saturn, and there was another mission. So it was during flyby, and they observed the moon for the first time in the 3 micron band, in the 3 micron domain. And they found this absorption here. And what you might know this absorption when you do infrared observations through the Earth atmosphere, because they are known as telluric absorption from water vapor. So they block incoming light. And yeah, that is a water H2O or hydroxyl OH band. That was very surprising in 2009. And since then, a large part of the lunar community tries to understand what we really see here. And we also tried to do that. And this is now simply a map of the depth of the 3 micron band on the moon after doing that thermal correction. And as you can see, there are, when there is no color, then there is no data. The bluer, the more water and or hydroxyl. And you can see now that was lunar morning, now it's lunar midday. At lunar midday, we have an especially high contrast between Maria and highlands. So there is some compositional dependence clearly. And when we go to the evening, we will see that the situation gets back to morning again, more or less. Yes, no. And you can see there is again a latitudinal dependence here. Like in the morning, okay, this is afternoon. Okay, here this is the latitudinal dependence near the poles. There is simply more of this. There's a stronger 3 micron band. Okay. I don't want to go into detail regarding the processes causing this hydration, because there seems to be even some clear dependence on on local time of day. Here, these are similar maps that we obtained with the very latest version of our thermal correction. You see that developing something like that takes, it took 7 years at least, and more than one PhD thesis. It's really not easy. And so you can see that there is a diurnal dependence, and what is the reason? The current assumption is that protons from the solar wind impact into the lunar surface material and liberate oxygen from the surface material. There's much oxygen in lunar minerals. The silicates are oxygen rich. On the Earth, on the Moon, doesn't matter. And then this oxygen, or part of it, can react with those protons, because protons are nothing else than hydrogen atoms without an electron, and they may form OH. They may also form H2O, but that would require, in that way of thinking, it would require one O atom finding 2 hydrogen atoms at the same time. So it's not clear if what we see here is due to hydroxyl or if it's due to water. So when you read about lunar water in the press, then hardly ever anybody cares about if that is really lunar water or just hydroxyl. And hydroxyl can be implanted in minerals in many forms. These are the so-called hydrated minerals. And at noon, here you can see, although the lunar surface gets very warm, and if you model such processes as we did with realistic physical parameters, you would find that the model would predict, or all models that I know of predict, that the oxygen disappears during the lunar day, which it doesn't. So most probably, at least that's what we proposed in our paper of 2017, there may be a stationary or strongly bounded component that's not necessarily magmatic or so, but just hydroxyl that has migrated into binding states that have a higher energy, a higher binding energy. So binding states, I assume you're all physicists, so you know that binding states corresponding to that oncoming and disappearing hydration component have energies of a few tenths of an electron volt, whereas one would need maybe 2 electron volt in order to keep the hydroxyl attached to the surface material for centuries. So everything is so that this binding energy has an extremely strong influence on how the hydration behaves. But this is all not really well understood so far, but it seems that this solar wind implantation mechanism can explain what we see here. But the resulting weight fraction, ppm, of hydration is really low, so it's not in the way that we have. So we didn't find nearly percents of water in the lunar surface material as some others found, but only maybe a few ppms. You can decide by yourself what you find more realistic. At NASA, there is the dream of having that in the surface material, because then the astronauts have something to drink, but I computed the amount of material you have to take, and you have to take the material from the surface of a large city, 20 by 20 kilometers, for example. And if you take that material and extract all the hydroxyl out of it, or no, it must be water. So and you extract all the water out of it, then you get a glass full of water. So that's not really suitable to provide water to the crew of a lunar habitat. That has been studied by various authors. As I said, I don't want to go into detail here, but I just don't want to act as if we were the only ones. The latest observations, which were independent of the spacecraft observations, by Honeyball et al. In 2021. They used a spectrometer in the one of the observatoriums in Hawaii. They found changes of the 3-micron band depth with latitude and local time, completely independent data in a form that is very similar to our findings. That was very reassuring for us. And now I will give a very quick introduction to the analysis of the surface structure by imaging polarimetry, because that's why we are here. I don't present any of our new results because they need some extensive analysis, I would say. The instruments we used so far are surprisingly small. That's a 200 millimeter aperture Newton telescope near Dortmund. To be honest, in my garden, because that was the first instrument to test the camera we are using. That's a highly innovative industrial polarization camera, which works in the way that each pixel has a little polarization filter attached to it, and each 2x2 block of pixels gives then enough information to compute Stokes vector, a linear polarization parameters. And last year, I did together with my colleague Mega Bhatt at PRL in Ahmedabad an observation campaign with a 430 millimeter telescope at Mount Abu Observatory in Rajasthan. In both campaigns, the imaging, the camera and the filter set was the same, standard UBVRI. Ground sampling interval of the polarization images is 900 meter. Phase angle range for the moon is between 4 and 108 degrees. And we have done our best to do georeferencing of the images in order to be able to put them into an absolute coordinate system and can superpose them on spacecraft data, for example. That is how the polarization behavior of the moon looks like. That's already known for some time. So these data are from Lyon, 1929. There is a maximum of the degree of polarization, which is denoted P here, at about 90-degree phase angle, half moon. And for larger and smaller phase angles, it decreases. And then happens something strange. The polarization degree becomes 0 at about 23 degrees phase angle. And then we get this so-called negative branch of polarization. This here is relatively well understood. Spherical particles behave that way, but they reach a polarization degree of 1 at 90-degree phase angle. And if you have anisotropic particles that will and multiple scattering, that will bring down increasingly the polarization degree. This negative polarization branch is not well understood. That's why we are looking at it here now empirically, because currently is full moon, so we are observing around full moon in this phase angle range. The good thing about these data is this negative polarization data is they have been observed for a multitude of asteroids and comets. So one can compare our results directly to those results and can at least say, okay, asteroids have a different surface or the same as the moon. These are typical results here. This is intensity and the degree of polarization. You see that there is some kind of inverse correlation between albedo and degree of polarization, and the angle of polarization, it changes by very small amounts, but that can also be artificial. We are not yet sure, just showing it. These are parameters at small phase angles. For example, the absolute value of the minimum polarization, which this is very low, that is just 2%, so that's not really easy to measure. And the phase angle at which the minimum polarization occurs, around 10 degrees. Here, the phase angle of inversion, that is exactly where the polarization degree becomes 0. There seems to be some correlation with structures on the surface. And this is here the lower right panel is the slope of the P of alpha function at the phase angle of inversion. That's a very important measure, by the way, also for asteroids and comets. And for 3 of these 4 parameters, we see correlations with surface structures. And one thing that one can do is to plot the polarization degree against the intensity or the albedo. If we do that, we get more or less a power law, so a straight line in that double logarithmic diagram, but we also get points that deviate from the fitted line. And deviations from that line have been interpreted in the famous paper by Skuratov et al. More than 30 years ago in terms of varying grain size. So here, larger polarization degree than expected, coarse grains, otherwise fine grains. And these are the grain size maps that we get. So it's not clear exactly what grain size. If it's the average grain size, there are hints that it's rather the grain size of the finest fraction. So if you take away the finest fraction of the regolith, then that might also increase the apparent grain size. But you can see here, there is a clear dependence. Here you see crater rays, for example, that have a reduced grain size. I don't know how well visible that is. The swirl that Deepak was talking about, Reiner Gamma, this slightly enigmatic and not topographically appearing structure has a decreased grain size, whereas volcanic pyroclastic material appears here as bright, so as more causally grained than the surrounding surface. And also here a small impact crater near the crater Atlas appears causally grained, probably because it's fresh, but there's also a causally grained pyroclastic deposit in the south of Atlas. This is Atlas crater, and here also in the north. So it seems that certain terrain types, at least as long as we know something about their formation, we can say that have polarization properties that are explainable in such terms. And again, a little bit of machine learning. Since we had a wealth of data and didn't really look where to begin, we applied rather standard methods, namely principal component analysis, followed by clustering, also known as unsupervised learning, with a self-organizing map, classical algorithm from the 1980s. But modern ones are also not better. At large phase angles, we can see this is again the Reiner Gamma area here. This is Reiner Gamma. It is a cluster of its own. So the Mare surface falls into different characteristics whose prototypical behaviors are shown here. So each cluster color here corresponds to the line colors here. So there's a range of polarization behaviors, and this is the polarization degree independence of wavelength, UBVRI. Here for the same for the area with the volcanic pyroclastic material, which also comes out nicely. The Atlas crater doesn't, it is not always very nice. So here under this phase angles, all the spectra more or less look the same and are not really well distinguishable. At small phase angles, this is the region with the pyroclastic deposits again. We can see that pyroclastic material stands out in those small phase angle polarimetric parameters as a cluster of its own in brown, surrounded by Mare material in red. And so also these parameters are closely related to the terrain form, and that has not been elaborated in detail in this way before, although lunar polarimetry is actually not a really young field. Okay, so that is what we can do. It's not in the way that we can say here, the regolith has this or that porosity and this or that. Yeah, the grain size we can estimate, but don't know to which size fraction it refers. So that means all in all, to summarize, visual and near-infrared orbital reflectance spectra in combination with gamma-ray spectroscopy data allow for mapping the abundances of key mineral-forming elements at a high spatial resolution. That is very useful, and that is nowadays done routinely. And I've shown that accurately modeling the thermal behavior of the lunar regolith is of crucial importance if you want to look at wavelength domains where thermal emission becomes important. For Mercury, high temperature, it's nearly everywhere. For the Moon, it begins at 2.5 micron. For us asteroids, maybe only at 3.5 micron. I don't know, depends on the distance of the asteroid from the Sun, but one has to be aware that without such a correction, all analysis is meaningless. And last point was imaging polarimetry is a promising method to obtain insights into the fine structure of the lunar regolith. One can use it to estimate grain size. One might also use it to estimate something like porosity, so how fluffy or how densely packed the surface is. And the physical understanding is still not good, surprisingly. So there simply don't exist good models to simulate scattering or to simulate the polarization of scattered light by grains with a complicated shape. So that is really required to better relate observational data to structural regolith parameters. Of course, laboratory analysis would also be great. Yeah, and that's how I would conclude. Thank you very much.
Thank you very much. So if you have any questions, both the speakers are here. If you have any questions, please feel free to ask.
Well, I have several questions actually, but I'll ask a couple. So first question about your spectrum. So aren't there any telluric lines at the shorter wavelengths? Aren't there any telluric lines at the shorter wavelengths?
Telluric lines in the polarization?
No, you mentioned at the 3 micron, you have this telluric line.
Yes.
That's how you discover this hydroxyl line.
Yes, that's a good question. In the spacecraft data, some people claim to have found them, but no, it's not really so. It's not in the way that you really clearly see them. And again, it depends on the analysis method, if you see them or not, and that is always suspicious. So I would say no, at the moment they are not visible. But it's also known that the 3 micron band is also for asteroids the most pronounced water band. It's called water band there, but it's also may also be probably hydroxyl. For asteroids, you also don't see anything apart from that. Whereas for the Moon, there have been observations with an airborne observatory in the 6 micron range where water has an emission peak. And the authors claim that they have found something. So that water really exists, because that would be an independent confirmation. But I know what do you mean? The shorter wavelength telluric line are not really present in the lunar spacecraft.
So regarding the diurnal variation of this absorption depth, so that you mentioned that is because of the proton influx, and then you see the decay of these hydroxyl ions. So then, I mean, perhaps you can model the amount of flux coming in and the amount of absorption missing from the sun.
That is what we have done. I just didn't want to put that into the talk. You can model it, and that is a really
that matches.
Yeah, that's exactly it, because there are many competing processes at work. In the very early morning when the sun rises, the surface is still cool, so OH can form and doesn't immediately evaporate. Then when the sun rises further, still OH may be formed, but with increasing temperature and the dependence is strongly nonlinear, it starts to evaporate very strongly. So that leads to a decrease. And only when the temperature in the afternoon becomes low again, then then the formation might be dominant. So it's a complicated interplay of destruction and formation mechanisms. And then on top of that, we have a rough surface where some parts may be hidden from the sun and other parts may be tilted towards the sun. So there is a lot of complexity in it.
Oh, thank you very much. I have, a couple of other questions if I may ask. If there are any other questions, maybe otherwise. Yeah.
So, for these observations, you're observing the means imaging for the complete moon or for specific parts of the moon?
This is clearly specific parts of the moon. With the smaller telescopes, one can cover several hundreds by several hundreds of kilometers with that camera. And with the telescope here, it has 13-meter focal length. So we have something like 200 by 200 kilometer region size. So that's why we are here. We are focusing on objects that are also similar, who seem to be of the sphere class. No topographic expression, bright, have been described in a paper 10 years ago, and nobody cared about it because moon is not so. So these things are, they cannot really be observed from spacecraft because one needs polarization data, and that is not yet available. So yes, and at the moment we are trying to get as high as possible resolution data for specific lunar features of interest. Full moon has been observed by the Ukrainian group around Yuri Shkuratov already 30 years ago.
More questions? I'll ask in the first part, I have a couple of questions. So you mentioned what happens to the impacting object. So, you mentioned a central peak formation. Doesn't the impacting object influence in somehow the central peak formation? What happens to the impacting object after all?
Yeah, so the impacting object is generally coming at speeds of about 20 to 25 kilometers a second. So most of it gets destroyed, unless if it is made up of metal. So the way the impacting process happens, things can impact vertically or at an angle. If they come at a very low angle, then there are chances of some material being preserved. But in general, all of it gets destroyed. So the momentum gets transferred to the surface. The central uplift actually comes after the cavity is formed. So it's a rebound from depth.
Okay, I also want to ask on the small granular craters you mentioned, right? The small scale craters, very small scale craters.
Okay.
So is the process same or how are they formed?
Yeah, the process is same. It is just that the amount of energy that you are pumping into the ground, as it increases, the morphology of the crater changes because it has to accommodate that amount of energy. So it's a failure mechanism. Smaller amount of energy you are pumping into the ground, you get bowl-shaped craters. You increase the amount of energy, you get these craters, which are called as complex, which have terraces and central uplifts and melt. You go to even larger amount of energy, and then the craters actually give rise to multiple rings. So there are multiple circular rings, and in between complex and these multiple circular rings, there is a case where you have the central uplift as well as the rings. They are called peak ring basins. So it is accommodation of the energy by the target.
Thank you very much.
So in one of the image, you were showing the distribution of minerals, like with different colors. So what it indicates, like?
So basically, as both of us have shown, when you look at the surface of the moon in spectra, you are basically getting a wavelength intensity plot, where at some wavelengths, the intensity is low, at some wavelengths, the intensity is high. So from the physical basis, they give rise to absorption bands. And the colors are generally, they can be actually anything, but generally what we map is the depth of the absorption band, how deep are the absorption band, because that is kind of proportional to the abundance to a first order. Although if you have to quantify that, there are many other things that come into picture, but largely we are looking at the abundance. Here, like at this scale, it's 1.5 kilometer, right? So 1 pixel is about 1.5 kilometers across. So there you are basically looking at which is the dominant mineral.
In one of the craters,
Mhm.
there was a big crater, and then the distribution like green and blue, was shown with green and blue colors.
Yeah. Yeah, no problem.
Is this also indicating that how the minerals are like propagated inside that crater?
In some way, in the example that I showed, that surface was molten at some time, and the S-shaped structure actually suggests that the material flowed. So that is why I said that it is kind of surprising, and that's why it is also the only feature of its kind that if things were propagating, if minerals were interacting, then they should mix, but they don't seem to. Our understanding is that perhaps the green feature formed later within the same formation process, but in terms of the time interval, it formed after the floor was filled with melt. So on top of a molten material, this thing came, otherwise they should have mixed. And that is also something that is expected from the cratering perspective. Earlier on, people have suggested that this is called impact melt. So people have suggested that impact melt is homogeneous down to millimeter cube. And here we are seeing these differences at several kilometers. So yeah, there is some interaction, but probably in this case, there is a time difference, so they could not really interact much.
I have one question, Christian, about this negative polarization, degree of polarization.
Yeah.
So what could be the cause of this negative polarization degree? And do we get, apart from this asteroid and moon, and which type of the astronomical sources we generally get such type of
So the negative polarization,
Yes.
I must admit that there is not the explanation, so this is their why. So that has probably to do with the fact that planetary or asteroid surfaces are grainy and are very fluffy. That is, the surface is very porous. Asteroid surfaces are probably much more porous than the moon surface because asteroids only have microgravity, at least small asteroids. There is actually nearly no gravity. So what should press the material together? On the moon, there is more gravity, but still electric charging of the grains may build up very thin structures that are called fairy castle structures. And so the thinner the material becomes, the smaller the filling factor in a way becomes, the more pronounced this negative polarization is. But it's on the other hand, if you measure polarization of a powder in a laboratory, just a loose powder, then you also see it. So that what I just said cannot be the explanation. And there is none at the moment. It's just there. And we see some correlations with grain size and especially porosity and also with the degree of anisotropy of the grains. So spherical grains most probably would not show it as far as I know. And why it's favorable to be measured is, first of all, because you might ask, why do you measure it when you can't explain it? We measure it because we can't explain it, because only with measurements it's possible to develop models. If you model it, you get something, and if there's no data to compare, then who can tell if the model is wrong or not? And asteroids have a very similar behavior, and there are various types of asteroids spectrally, and the same types of asteroids can be can be found in the negative polarization parameters. That is very interesting. So it makes, so it's not like a laboratory confirmation, but it's like we have objects for comparison. And that's why it's really interesting to look at. But we would actually need laboratory studies in that range for regolith-like materials, which are very difficult to prepare on the Earth, because Earth has strong gravity. One would actually have to do it under a microgravity. Maybe on the ISS, I don't know, but probably that's a bit too esoteric for those. That's one thing, and of course, physical modeling of scattering processes, which becomes just now possible because if we compose very complicated, anisotropic, thin structures, which may consist of little spheres, but effectively the big thing is not spheres, then one might get a step further.
Okay, thank you. So if any question, no question, further question, let us thank both the speakers. Yeah, thank you very much.